Beginning of all the talks, I think all the speakers have had to introduce themselves. It seems like there is a core group of people here who really have lived much of their careers in problems that have to do with interferometry, and a number of us who all declare ourselves as outliers when we arrive. So let me explain a little bit about who I am and why I'm here, because I am not going to talk to you about an outlying subject. This is about interferometry and about an interference phenomenon. I'm on the faculty at UC Davis, but my research grants and my research group are resident at the Lawrence Berkeley National Laboratory next to the Berkeley campus, where I am the titular head, as a theoretician, the titular head of the ultrafast X-ray science laboratory. And I say titular because the experimentalists don't listen to me at all. They won't let me tell them what kind of laser to buy, and they won't let me touch one either. So, but they will let me do all the paperwork for them. And so frequently as I'm driving, these 2 points are 70 miles apart, and frequently as I'm driving back and forth between them, which I do almost every day, I feel that when I'm neither in one place nor the other, but in both places simultaneously, that I have a really good insight into the psychology of Schrodinger's cat, if not to the actual superposition phenomenon. So let me start by bringing Coles to Newcastle. And that is to remind you about a set of papers that, and ideas that at least one or two members of the audience have no need to be reminded of. And that's the idea of two-particle interferometry. And I took a figure from a paper by Kurt Gottfried, which is a pedagogical paper in the American Journal of Physics. And the idea is the following. Does somebody have a laser I can borrow? Somehow I say that all the time. Oh, thank you. I say that all the time. The experimentalists keep saying no. So the idea is that you have in the, well, this is like one of the lasers they complain about that doesn't have enough power. So the idea is that you have an atom in the center of this, localized in some way. It undergoes a fragmentation which is momentum conserving into a pair of fragments A and B. And the momentum conservation is important because that's why the momenta of the two fragments are entangled when they leave. And they go essentially back to back then. And then you catch the two particles in coincidence. So everything about two-particle interferometry is an interference pattern that shows up in a coincidence measurement. You catch them in coincidence at distant points on these screens at opposite sides. You put a pair of slits in between, which is important, and so you look at, this is really pretty weak. Does somebody have one of those nice green ones? Oh, yes. That's right. You see, if you just annoy the experimentalists long enough, they'll actually... So, yes, excellent. So, so the idea is that with evaluating the wave function on the screens in this conditional joint probability, that you'll see an interference pattern that comes from the entanglement. And the entanglement's essential, the fact that it goes back to back, and that in fact that the only amplitudes that survive is one particle going through RA and the other going through RB, or one going through RB and the other going through RA. So when you integrate out one of these two, you see no interference pattern, and if you do the coincidence measurement, you see both. And this idea, as far as I know, came originally from Mike Horn, who's here. That's why I really feel like I'm bringing Coles to Newcastle. And you can't see Dan Greenberger's name down here at the lowest reference. This idea is an old idea. It's been here for a long time. So this idea was sort of realized in a Physrev letter in 1998 and suggested by Joe Maychek in photoionization of atoms that undergo Auger decay. So to remind you, I don't know why the little sound thing keeps coming up. To remind you what Auger decay is, you knock an electron out with a photon from an inner orbital, and then having done that, let me remove that annoying little beep. There we go. Having done that, the molecule, I guess the little beep is not going to go away. The atom or molecule is in a highly excited autoionizing state, and electron then can fall down to occupy the core hole that you've just made, and another electron goes out. And the idea of the experiment was to tune the photon energy to make the energies of the two electrons essentially the same. And then having done that, you could do a coincidence measurement. You don't know which is the Auger electron and which is the core electron. And this little smudge here was enough to get into Physrev letters. I think Professor Volkoff was talking about the status of papers as not yet rejected from Physrev letters. We should have a talk about that. So But this little smudge is a part of that interference pattern. And so they declared that they had seen this, and that was victory. So I'm a theoretician, and what I'm going to talk about is a kind of two-particle interference in a somewhat different domain, but having to do with electrons. So I need to take you on a little excursion, because this was not something that we had planned, and I need to take you on an excursion to accomplish two things. One, what I'm going to show you are not model calculations. They're exact solutions of a three-body Schrodinger equation, and that's why we have confidence in the robustness of this effect. So I need to try to convince you that that's something that we can do for double ionization. And the other thing is to give you an idea of the context of why anybody would have been working on these problems to begin with. So you might think, I didn't, that you might see two-particle interference in double photoionization of atoms by one or more photons in some more interference pattern-like way than what we just saw. And the reason that there are people working in this field is it's now possible to do coincidence measurements of double photoejection that look like this. The methods are globally called momentum imaging methods. They have position-sensitive and time-sensitive detectors on either side. There are these interesting mats of wires that cost a fortune and that were originally fabricated, I think, in Frankfurt. And the idea is that you have an ionization event that singly or doubly ionizes an atom or molecule, a molecule in this case, and electric and coaxial electric and magnetic fields sweep the charged particles, the positively charged particles, to one side, the negatively charged particles to the other, and you see one electron undergoing its cyclotron motion as it hits. With the combination of Jackson's book on electrodynamics and Goldstein's book on classical mechanics, any good graduate student can figure out several things from the times and positions of the hits. And the times and positions of the hits tell you even the orientation of the molecule at the time the event was done. They do these experiments tens of thousands or hundreds of thousands of times taking data, and they mine the data set for specific orientations in space of the molecule, or if it's just two electrons coming out, they mine the data set in order to get a complete correlated coincidence measurement of the angular and energy dependencies of the two electrons going out. This is a technology that's been going for about 20 years. You can also accomplish double photoejection by ultra-short XUV pulses, and that's where we're going in this talk. But of course, in order to solve this problem, one has to solve the three-body Coulomb breakup problem at a minimum, right? So that's three charged particles separating. That's a notoriously difficult problem. And it now is pretty much in hand. We can do this, for example, for H2+. Not only we, but there are 4 or 5 groups in the world who can do this. The reason that people are interested in this is that one photon double ionization has to be a probe of electron correlation. The dipole operator is a one-body operator. It's talking to one electron at a time. If more than one electron leaves, they have to have been talking to one another. So they have to share the energy of that photon. And so the idea of these experiments is to probe electron correlation. And to probe it in molecules and to understand something about electron dynamics. And that's if you will, the raison d'etre for the whole field. We've done, this is just an existence proof of comparison with experiment. Even to things like changing the internuclear distance of the molecule. I seem to have the same effect on lasers here that I do in Berkeley. Even with respect to the internuclear distance of the molecule, which you can see in these experiments, you can watch the coincidence measurement of the conditional angular dependence of the two electrons change in space. And so it's really quite interesting to do. Now, the way that we solve this problem, and this is part of my attempt to convince you that we can solve this problem exactly numerically. The difficulty is the boundary conditions. And this is I'm one of the, I think, 2 theory talks here. Is that right?
There's a couple more.
Oh, they're good. All right. So you feel a little, ITAMP, feel a little lonely.
Yeah.
You know, it's unusual in an ITAMP workshop, right, to be one of the few theoreticians. So this is an expression of part of the Coulomb boundary condition, and it has the usual logarithmic phases, but they vary with the directions of the ejection of the electrons and with their energy ratio. So this is a notoriously difficult thing. It's never been applied, as far as I know, directly in a matching way in a calculation on ionization. But starting from an idea that I believe actually began more or less here at Harvard in Bill Reinhardt's research group, which was to analytically continue the coordinates of the electrons in the Hamiltonian, in our case, a later twist outside of some radius R0, you take these pure outgoing boundary conditions, regardless of how complicated they are, and you render them essentially totally benign. Any outgoing wave, think of e to the IKR, e to the IKR over r, as soon as you start looking at it on an array like this, dies off exponentially. So that converts miserably complicated boundary conditions into goes to zero, right? Goes to zero is something we can deal with, and we can deal with it in very large calculations. We can do these analytic continuations of the Hamiltonian in two coordinates. And what you get are wave functions inside that R0 region, and we solve these problems on grids. We get the Schrodinger equation. This is the one for the first order wave function for photoionization by one photon. They're large matrices. They'll be of the order of 1 million by 1 million, but they're sparse. These are big supercomputer calculations, even for two-electron systems. But what you're able to see in the wave function, wake up, you're able to see single ionization. These are different angular momentum components of the wave function as a function of the two distances of the electrons, R1 and R2 here. You're able to see along the edges single ionization, and in the middle, you're able to see double ionization, these ripples in a pond, where both electron coordinates are getting large. So we've been able to solve essentially all the two-electron problems. There are other ways to do this, but I'm talking just about our work at this point. And then we can extract this amplitude, the object of our desire, this joint probability distribution, by just a surface integral with a testing function that extracts this amplitude by a sort of stationary phase phenomenon. So that's how we solve the problem, and we can solve it essentially exactly. Now, where this field went immediately, of course, was with intense sources, was to multiphoton ultraviolet and X-ray absorption. And in that case, you've got a couple of different possibilities. So this is energy levels of the helium atom, and keep this simple. Ground state of helium, helium plus the monocation, its excited states, and finally the double continuum. So if you have two photons whose energy is sufficient in sum to double ionize, you have to, then you can have non-sequential absorption of the two photons. Both the photons are eaten simultaneously. The two electrons then share the outgoing the excess energy. If you have enough energy in the photons, then you can have the sequential absorption. You can ionize the atom first, and then ionize the ion with the second one. And then you should have sharp electron energies that correspond to the two processes. This is a simple idea. Those two processes have to compete, of course, at higher energies. And this whole issue of sequential and non-sequential ionization, and if we have more than one photon absorbed, how the two compete and how they change with intensity, that's where the field was going, or is going, has gone. Now, something else happened along the way. Right? And that is the ultrafast revolution. So there's a wonderful article in Reviews of Modern Physics by Ferenc Krauss and Misha Ivanov about high harmonic generation, in which you take a gas jet, you subject it to a very intense infrared laser. This is a wave packet being drawn out and repeatedly recollided with the atom. What comes out of this are high harmonics of that, say, 1.5 volt fundamental. So you can get up into the UV, into the XUV with those high harmonics. But they come out, and this is the point, they come out in short bursts every time the IR pulse re-accelerates the wave packet across the atom. So they come out in bursts of about, 500 attoseconds or so. And these are images of the IR pulse being used as a streaking camera to image electrons that are being launched by one of these attosecond pulse trains. So this is on top of what I just showed you. So this is, of course, where we all went. In this field, now we want to figure out what happens after the pulse is over. After the pulse is over, the electrons are still interacting, but they already know where they're going. The amplitudes, this is the object of our desire of launching the electron into a double continuum state with momenta K1 and K2 are already defined. And this little trick that I showed you is one that we can use to extract those amplitudes as well. We want to propagate all the way to infinite times and then Fourier transform it. We can do that in one step with this exterior complex scaling idea, solving a linear equation where the driving term is the pulse, is the wave function at the end of the pulses. So trust me, we can do this. This is not a model. Now let's talk about the subject. All right, so first, what happens if you take a really this is something, I'm watching the time here. This is just showing that, for example, if we take a short pulse with two for absorbing 2 photons and land on the autoionizing states of helium, we can see them, extract the amplitudes, and see the whole sequence of autoionizing states as it converges up to the helium double plus threshold. So we can essentially analyze the wave packet and resolve exactly what's going on in the final state. So in one photon double ionization, I'm sorry, one color, 2 photon double ionization of helium. There's a huge literature. There's a little piece of the literature. Almost none of it time resolved because these time resolved sources didn't exist for much of this time, or at least weren't intense enough to do any experiments with. Johannes Feist and Joachim Bergdorfer. Johannes Feist is one of the ITAMP postdocs. He's here someplace, I'm sure. Hi, Johannes. I've written a couple of papers in this area doing work very similar to what I'm describing here. There are a couple of experiments just on the magnitude. So what happens if you take a short pulse, I'll say a couple of femtoseconds long, 40 to 55 EV, 40 to 60 EV, about 10 to the 12th watts per square centimeter. Do you see anything different because the pulse is short? This is a review of what sequential and non-sequential is, so I'll just skip through this. Well, these are, the thing that you're looking at is a joint energy distribution. We measure the electrons in coincidence, and I'm plotting the ratio of the energy of one of them to the total energy of the pair. And of course, that plot has to be symmetric, and as you approach the sequential ionization threshold from below, the energy sharing distribution, we're going to see a number of these. This is where we're going to see this interference pattern. The energy sharing distribution becomes more and more peaked, with electron 1 going out fast and electron 2, this always has to be symmetric, going out slowly. And then when you get above the threshold, you see a pair of these peaks. And as the repulses get longer, you resolve them better. As the repulses get shorter, it looks like you make the sequential process go away. Right? It's not quite right. This is mostly Fourier broadening, but it's at least partially right to say that, that you're modifying the dynamics. And if you look at the angular dependencies, you can see that below the threshold for, have I killed it? It's amazing. This is why they don't let me touch lasers. This is why they shake it. You can, if I were to do this, and you have any? Yeah. All right, that's it. That's it. It's the, I guess. All right, back to the weak laser. Right. So if you look at the angular dependencies in the non-sequential region, they have to be back-to-back. In the sequential region, they look mostly like a pair of dipole patterns. By region, I mean the energy. But if you make the pulse short enough, even at 58 volts, well above the sequential threshold, you can make them go out back-to-back. They're launched so rapidly that they have to be interacting at the time that they're launched. Oh. So you needed a real theoretician to fix it. And I didn't mention that the bottom of that slide, let's see if I can go back. Can I go back? Yeah. This is also work that Johannes Feist and his colleagues published in PhysRev Letters at the same time that we found the same results. All right, now here we go. This is the center of the talk. Now, time-delayed 2-photon ionization that is sequential. We take a pair of pulses. And here's what we were trying to do. Those doubly excited states of helium have an entire literature that goes with them. By literature, I mean there's like 50 papers on them. And because they look like a triatomic molecule. The 2 electrons get to opposite sides of the helium atom. They're perfectly correlated with each other almost. I mean, this is sort of electron correlation heaven, right? Because you have this really tightly correlated system, but it's only a pair of electrons. And that's what we were trying to do. They start around this energy, around 69 volts. And we were probing those and trying to ionize them again, tickle them with another UV photon. And you get, in this particular case, for this particular pair where we first saw this effect, you get what you expect. The first photon can ionize a helium atom and excite it at the same time. That makes these 2 sequential peaks. The second electron comes along and ionizes it. And in the energy sharing distribution, the joint profile, you see a pair of sequential peaks. Now something, I haven't learned much from the experimentalists, but something I have learned is doing a pump probe experiment, you take the probe and you put it first and the pump and you put it second, and you're supposed to see nothing, right? So we were doing that, right? And when we did, right, we have now the 35 volt photon comes first and the 69 volt photon comes second. There's a hint here, the energy distributions of those electrons can overlap. Then we see this. We see if with no delay between the 2 pulses, we see just a single lump. As we increase the delay between the 2 pulses, we see this interference pattern showing up. Now, that was something which we didn't expect, and I didn't believe. And so we tried to make this go away. And I can tell you this is a really robust phenomenon, right? And it's also a zero background experiment, because in this double ionization process, there's nothing else going on that can make two electrons, right? So
The horizontal axis?
the horizontal axis is energy sharing again. So this is the fraction of energy that electron 1 has. That's why it's always symmetric. You're going to see this in a different form here in a second. Now, as I said, the wave packets have some amplitude. I mean, some amplitude here, written in atomic units, is a plot of the joint energy distribution. Now, not just a cut through it, but the whole thing. So every point on this graph, I've got an electron of energy E1 and energy E2, and you see these interference patterns building up as the two times are separated. And the oscillations are almost, but not quite, at delta E being the full period, 2 pi over the time delay of the pulses. It's robust to the type of pulse. These are in the sense that if you use Gaussian pulses instead of sine squared pulses, everything looks the same except the line shapes. So what's happening? Now, I said this is bringing coals to Newcastle, but I want to sort of rub in this idea, right? Which is, what's happening is that so let's look at it with just time-dependent perturbation theory. In time-dependent perturbation theory, I'm going to keep only, now this is a model, not the exact calculation, I'm going to keep only the singly ionized states that leave helium behind in its ground state. So the first amplitude is to singly ionize. There's an energy difference times time that goes with that factor. And then the second amplitude is to doubly ionize by having ionized that step. There's its energy difference. And then we have a product of the field, and the field has both pulses in it. Now, in the final state, we select the dumbest model that we can think of. And the dumbest model is take a product of 2 Coulomb functions. The final state has to have the same spin coupling as the initial state, right? And the initial state is a singlet, and so we have to have singlet spin coupling. Therefore, the space wave function has to be symmetric. You know where this is going. You put this in, you make another really dumb approximation. That is that you pretend that the electron in the intermediate state sees a charge of 2, and then a momentum-conserving delta function does this integral, and the final result that you get is a sum of 2 terms that are going to interfere. Amplitudes for ionizing the system, a pair of Fourier transforms of the pulses, and this expression is basically the sum of 2 processes. Electron 1 being launched by the first pulse from the neutral, and electron 2 being launched by the second pulse from the ion, or the reverse, where electron 2 is launched first and electron 1 is launched second. Not so much of a surprise. The surprise is that you can see it. And then you can make even simpler approximations by using the experimental single photoionization amplitudes and taking the square root, ignore that phase altogether, ignore the phases of these products of Fourier transforms, and then the relative phase is just, with the factor of h bar missing, is just the energy difference between the 2 electrons times the time delay. Now, this is the slide that I showed you before. That ultra-dumb model does this, right? Let me rock it back and forth. Unfortunately, I'm still seeing this. What you see, whoops. It doesn't perfectly match all the results. It gets the spacing right. It gets the line shapes quite a bit wrong. But it carries essentially all the physics. There's more information in this interference pattern, is my point, in the line shapes. But the basic physics is that this is a 2-time interference process. So the pulse, varying the delay, controls the fringes, how many fringes we actually have, right? But varying the pulse duration controls the interference interval. So if we have, this is with a time delay of 500 attoseconds, and this is a time delay of 1 femtosecond. If we vary the pulse duration, the pulses get narrower and narrower in energy, and then the region over which we see the interference pattern decreases, right? Different frequency and of this, and it decreases. We can control the contrast interval and so forth by varying other contrast ratio, by varying other aspects of the pulses. But in all these experiments that we did, all these numerical experiments, this is a totally robust effect. I mean, it doesn't, you know, it's something that has to do with the antisymmetry of the wave function, and not the correlation between them. That's an interesting difference in the way that we use those words. I'll mention that in just a second. If you look at the angular distributions, these 2 electrons still know about one another. The time scales are short. They're still trying to go out back to back. So what we would say is that they are correlated, the two electrons are correlated. It's going back to Paraloff-Lubdin's definition of correlation and of correlation energy, which is the difference between the mean field or Hartree-Fock approximation and reality. And we only see that here, but we see their entanglement in this interference pattern. And they're entangled whether they're correlated or not in the language that we would use. All right, so I ran down the hall, right? We have a bunch of experimentalists. They have high harmonic generators. Steve Leone is there. Ali Belkacem is there. I ran down the hall. I shouldn't have named them. I said I wouldn't, right? So let's do this experiment. Well, what will I learn if I do it? Right? What part of quantum mechanics did you think wasn't going to work this time, right? Just because nobody's done this before, right? That was the first, that's right. We don't have enough photons in the harmonics near 70 volts. Okay, I can't argue with that. We will later. We need higher repetition rates. This is a coincidence experiment. A coincidence experiment, you need to have about one event per shot, but you want lots of shots, right? So send money, right? I hear that frequently. And also, can't you find this in a more experiment-friendly system? You know, helium has the highest ionization. It's the most inert atom. It has the highest ionization potential of anything, right? And so, consequently, we need the highest photons. Well, I can't. Well, I didn't give money, but I think I can start trying to answer numbers 1 and 2, and maybe with your help, we can think of other reasons why this experiment can be done, because they're entirely. They're at the edge of what's within reach, but they're entirely with what's reachable, I think. Now. So the electron pairs that we double ionize out of a many electron target are now entangled in a different way, or in an additional way. They have to be entangled with one another. They have a spin state that's an observable final state. But the atom that you left behind, if it's a many electron atom, now has its own spin states. The overall spin state of what you detect and what's left behind in the target have to still be entangled with one another in such a way that they produce the same initial spin state that we began with. Come on. I pushed the wrong button. Come out of this. Come on. No, we don't. Come on, come on, come on. Get out of this. Oh, all right. Let's see. What am I going to do to make this thing go away? I know. Let's see here. Escape again. There we go. All right. Let's get back. All right. Are you going to work? Yes. So let's look at helium and at neon. Yes, those were. I think those were my children, weren't they, Bill? So let's see here. Neon starts in a singlet S state. You absorb 2 photons. Its lowest excited state is a triplet state, which means that if you make the neon triplet state, you have to make the 2 electrons triplet coupled. Shortly above that, as you're about to see, is the singlet state. If you make 2 electrons there, they're singlet coupled back to make an overall singlet, but they have to be a singlet themselves. So I'll try to press only one button this time. So let's look at the energetics. This is more experiment friendly because now the ionization potential of the intermediate is about 40 volts. So the 2 photons that we need are of the order of the 15th and 27th harmonic, something like that. For this, you'd have a small window of about 3 or 4 volts in which you would only make the triplet. You use the harmonics that are close to these frequencies. You make pulses that are a little longer than we had before, and you can separate them further. The cross-section, this is the window of that cross-section. There's a Rydberg series that goes across it, and there's a bunch of resonances there. They don't change any of these arguments. Right? They add a little more interest. And then you see this if you apply this model. So now we see the same set of interference fringes. I've made a bunch of approximations to the ionization amplitudes and done a raft of angular momentum coupling because they're intermediate angular momentum states, and you've got to make the coupling pattern that gets you to the final state, and that eliminates most of the intermediate, most of the possibilities. There are longer pulses here. There's up to 8, and also longer durations. We're getting much closer to what we can do experimentally right now. And this is something we can do experimentally right now. And the energy interval is about 4.5 volts, and so that means we only need about 1/10 of a volt or even less resolution to see this really strongly. So we did that. The other thing is that the peaks become valleys and the valleys become peaks. You can tell the spin state of what you left behind, right? Because now you've changed the coupling, spin coupling between the 2 outgoing electrons. Space wave function is now symmetric because it's a triplet state. spin wave function is symmetric because it's a triplet state. Space wave function is antisymmetric. So you've completely inverted this. A superposition of different patterns from different states would give you a superposition of two interference of patterns that eventually would be completely dephased and washed out. But before that, you would be able to see the different amplitudes for leaving the target behind in different spin states and no magnetic fields involved. All right, I'm almost done. How much time do I have?
9 minutes.
Oh, I'm going to finish way early. That's okay. I didn't have that long of a story to tell, and I always talk too fast. So, so we still haven't convinced them to do this experiment because they're living in an orthogonal world, right? The orthogonal world is we're interested in ultrafast phenomena and phenomena that are that will tell us something about electron correlation in molecules or electron dynamics in molecules. So that to get this high up on the list of things to do seems to be somewhat difficult. But what else might you be able to do with it? This slide was not, it could have been, but was not stimulated by Professor Tanimura's beautiful talk on electron interferometry a couple of days ago. But what happens if you were to do this? If you were to do this from a solid surface? I mean, we can certainly shine ultrafast pulses on a solid surface. You can certainly ionize a solid surface with them, easier even. Could you probe the spin couplings of a localized surface state? Or let's say you have a magnetic target. The spin density is in some magnetic domain. Spin density is what it is, right? So you have more spins aligned in that direction than in others. You ionize out of that part of the conduction band. The two electrons come out. Now it's mind-bending and probably wrong to think about an overall spin state of 10 to the 23rd electrons plus 2. But you can certainly use density matrix arguments to see that you must be launching electrons that are mostly spin parallel. Is this a really easy way to do this with the fifth harmonic, right? And where you would be able to see the existence of the spin domains and so forth. I don't know, and my solid state friends always scratch their heads when I ask them this question. But this is a robust phenomenon as far as we can tell. I mean, in any calculation that we do, once you see it, it doesn't go away. It doesn't depend very much on the pulse durations. You can be much sloppier with the cleanness of the pulse or its shape and so forth than we've been here in the theoretical calculations, and you still see it. So what I hope that I've been able to show you is that we have seen this, seen it in the sense that, you know, we're theoreticians and we solve the Schrodinger equation exactly, and Johannes Weiss feels the same way that I do. We're writing a paper with a bunch of experimentalists who do this, and, you know, we're right and, you know, they're wrong always, right? So we know because we know what we're doing, right? So it's a two-electron system. We can be arrogant in that sense as theoreticians, an arrogance which we don't have for many electron problems beyond this. So this is there. It's robust. In more complicated targets, the two-electron interference phenomenon involves entanglement of that pair of electrons back with the target, which is kind of an interesting twist as well, especially if you could see it so easily. I believe these experiments are doable with the current technology if they were to be a priority. If the Department of Energy were to be interested in interference phenomena as opposed to electron dynamics and energy, right, that I think this would be entirely doable. And I think, after talking with Mike Horn, this might be the first time that with heavy, that means, you know, not photons, particles, that you would see this two-particle interference in time. It's not a surprise to the core group here that you would see that. What was a surprise to us was that it's such a strong phenomenon in this case, and apparently so easy to see, whereas the spatial version of it is so difficult to see and so difficult to realize with electrons. And so that's really all that I came to say, and I finished early, and maybe we can have an early coffee or something. So thank you very much. I appreciate the invitation.